This conference will now be recorded.
So very good evening, students. Today we have few questions on magnetism. These questions are from JEE Advanced papers 2021 and 2020. So let us solve this question. See, whenever we go for solving advanced questions, we have to remember that there can be more than one option correct. Okay, more than one options will be correct. So we have to be careful and try to answer correctly. Okay, so let us solve this problem. This is saying that a long straight wire carrying a current I is equal to 2 ampere. As you see, this is a long current carrying wire. So long current carrying wire is this one. A semicircular conducting rod is placed beside it on two conducting parallel rails of negligible resistance. So beside this wire, a semicircular rod, this one is the semicircular rod. As you see, this rod is placed on two parallel rail. These are also conductors. Okay, conducting rails. Conducting rails, they have negligible resistance. Now both the rails are parallel to the wire. See, this is rail 1, say this is rail 2. So this rail 1 and rail 2, they are parallel to the current carrying wire given here. Okay, the wire, the rod and the rails lie in the same horizontal plane as shown in the figure. So as you see in the figure, the rod, the wire, the rails all are in same plane. Two ends of the semicircular rod are at distances 1 centimeter and 4 centimeter from the wire. See, the ends of the semicircular rod are situated at 1 centimeter from the conducting wire, current carrying wire, and 4 centimeter. The other end is at 4 centimeter away from the wire. Now, at time t is equal to 0, the rod starts moving on the rails. See, you can see this. The rod is moving in this way. Rod is moving in this way on the on the rails, and the speed is given. Speed v is given as 3 meter per second. Okay, 3 meter per second, as you see in the figure. Okay, so the rod, this semicircular rod, is moving with velocity 3 meter per second, moving on the rails. That means the circuit is complete. You can see that a resistor R is equal to 1 ohm and a capacitor C0 is equal to 5 micro. So this is actually microfarad, not farad only. This is microfarad. Somehow it is missed. So C0 will be microfarad. Okay, so C0 is 5 microfarad are connected in series. Okay, so C0 is actually 5 microfarad, that we have to remember. 5 microfarad are connected in series between the rails. See this, these are rails. Between this R and C, they are connected in like in series combination. Okay, at t is equal to 0, C0 is uncharged. C0 was uncharged at t is equal to 0. Which of the following statements are correct or statement is correct? That means there can be more than one options correct, so that you have to find out. So you can see this is a question not only from, okay, this is actually from electromagnetic induction. This question is really from electromagnetic induction. Okay, so here we have picked up this, so we'll solve this question. You can see this is kind of, this is BVL, you know that this motional EMF, BVL. Okay, so we have to actually see the options. You see the maximum current through R, so you have to find out maximum current through R. So how to find out that? If you know the potential difference between the ends of the rod, then, or EMF develop across this ends of the rod, then you can find out E by R, that is the current. So you have to find out the current. So there are questions like what is the maximum current passing through this R resistor, and what is the maximum charge stored on the capacitor. So these are the questions. There are two questions are there. So what is the charge stored in this capacitor, and what is the current, maximum current flowing through this resistor? Okay, so this is actually from EM induction, even though it looks like from magnetism. Anyway, let us solve this problem, because we need actually knowledge of both, since it is the question from JEE advanced paper. So in advanced questions there will be no boundary that question will be from only from magnetism or only from EM induction. So when you learn the concept separately, that is fine. You will see some questions separately, but when you go for solving advanced question, so question will be mixed up. So you can get electricity magnetism together, electromagnetic induction magnetism together. Okay, so basically there is a very intimate relation between EM induction and like magnetism. So this question can be considered for both the chapters. Okay, all right. So what we have to do, we have to actually find out EMF, right? We know motion and EMF. What you can write? B V L. But here you look, what is the, or we can just go with this preliminary. EMF means d phi by dt. What is d phi? D phi. What is phi? Phi is the magnetic field, magnetic flux. Phi is the magnetic flux. Okay, so magnetic flux density into area. Okay, area divided by t. So this is finally the thing. Now you can remember simply that when we have a rod, straight rod, what we had done, like what we have written d EMF is equal to BV and dr. Do you remember this? So you might be remembering when a psych spoke, like, see, this is rotating and magnetic fields are perpendicular to this. So we have considered that at distance r, we have taken a small stripe. Okay, small stripe that is of thickness dr. Similarly, if we just want to find out, let us say elementary EMF develop across the semicircular so the EMF developed across the ends of the semicircular rod is given by C. Will write elementary. First, find out elementary EMF DE. DE is equal to what we had written B. Elementary means what? I'm just checking here. Suppose from the wire R, from the infinitely long wire at a R distance, I'm just taking an element of thickness dr. Okay, at R distance we are taking an element of thickness dr. This is dr, right? So what is the EMF? EMF for this particular strip or elemental area? So that is B, V and dr, right? B, V and dr. So what is B here? What is B? B is magnetic field at R distance, okay, at a distance R. So what we can write for a long straight wire, we know mu0 I by 2 pi R. So this is B, V and dr. Okay, look then, if we just integrate, see, semicircular arc is from here, 1, from the wire it is having distance R is equal to 1 centimeter to R is equal to 4 centimeter. So if we want to find out the total EMF developed across this wire, semicircular rod, that can be obtained by integrating this elementary EMF, that is 1 to 4, okay, 1 to 4 mu0 I by 2 pi R. So this is dV dr by R. Okay, now this will be mu0 I V by 2 pi, and this will be ln 4. So ln 4, this 4 can be written as so we can write this like this, and this 2 can be here. So that 2 and this 2, they will get cancel each other. So I'm just writing this as only ln2 and this one. Okay, so we have got EMF. Okay, EMF. Okay, so we have got the EMF now. So what is the EMF? Develop in this region, this develop across the end of the rod. So that is mu0 I V by pi into ln2. Okay, so now once we get this let us write this somewhere. We have got the EMF mu 0 I mu 0 I V by pi. This is ln2. Okay, this is the total EMF we get across. This develops across the end of the rod. So we have got the voltage. So we can now find out the current. What is the current? Current, the maximum current passing through R. The maximum current passing through or flowing through R. Passing through R. Passing through R is E by R. What is E? Mu 0 I V by pi into ln2. So this is the current. Now if we put the values appropriately, okay, if we put the values appropriately, like this mu 0 is 4.10⁻⁷, then I is 2 ampere given, V is 3 meter per second. Okay, and ln2 has a value nearly 0.7, and this is pi. So this would give you EMF. This would give you EMF 24 24 I'm sorry, this we can just put the values and then we can get the final value for this EMF. What is the value we get? So this is the EMF we have got. Now what is the current? Current is E by R. So I is equal to E by R. This is actually ampere. E by R. So R is 1.4 ohm. Very negligible resistance. Okay, so once you divide this with resistance, this is the EMF actually. This is the EMF so far. So current will be this by 1.4 into 10 to the power minus. So finally what we get, this value is, anyway, let me just write it properly. I'm getting confused. So this is 10 to the power minus 10, sorry, 8 volt. That is fine. Now let me just not get this here. E by R. So E is this 1.4 ohm. So this would give you nearly 1.2 10 to the power 2 microampere actually. So therefore the maximum charge stored will be oh sorry charge on capacitor. So this will be coming around 8.4 into 10 to the minus 12. Okay, so this is how this is farad. Sorry, this is charge means coulomb. Okay, so this is how you need to solve this first question. So we had option first one is correct. (8.4) this one, this is the answer. So A and C are the answers in this case. Now we'll try to solve the second question. So this question says an alpha particle of mass 4 mu and a singly charged sulfur ion having mass 32 mu are initially at rest. They are accelerated through a potential V, then allowed to pass into a region of uniform magnetic field which is normal to the velocity of the particles. Within this region, the particle and the sulfur ion move in circular orbits of orbit RA and RB respectively. Therefore, you have to find out what is the ratio of RS by RA. Okay, so you have to solve this problem. So the question I'll repeat once again. This is a very simple question, but sometimes you may feel it tough to understand by reading this many lines. So an alpha particle which has mass, so let us say alpha particle, it has mass m is equal to 4 mu. Then alpha particle mass charge q alpha is 2. Okay, and mass for alpha particle is okay. So these are the things given. Now you have to find out the expression for the ready. When a charged particle enters the region of electric field, sorry, uniform magnetic field, uniform magnetic field, so whenever there is a charge moving in a uniform magnetic field in a direction perpendicular to the field, then it will actually execute a circular motion. Okay, it will execute a circular motion, and you know there will be magnetic force QVB on the charged particle when it is moving with certain velocity, certain constant velocity. It will be experiencing a force, and that magnetic force will actually give it to the give the centripetal force to move in a circular path. Okay, so QVB is equal to mv square by r. Okay, so see here, so we can find out relation for this is actually mv by qv. Okay, so this is mv by qb, sorry, qb. So this is the expression for the now. This is the expression for the ready of the circular arc or circular path. And now we know kinetic energy is equal to, so kinetic energy is equal to half mv square, and if we equate this half mv square to q into v, that is the energy. So from here what we get, v square is equal to the 2 qv by m, 2 qv by m. Now we know that v will be actually square root of 2v, this is q actually, 2qv. Here there will be m also, m is down, right? So 2q v, 1v, this is voltage v, and this is by m. So if we put it here in the place of v, what we will get actually, we'll get r to be 2m 2m, sorry, so 2 mv by q. Q will be down. Okay, 2 mv by q. So this is, and here there will be 1 over b. So this is the expression for the radius. Now we have to find out the ratio. So what is RS? I can write this this is, suppose this is S suffix, there will be Vs. They both are actually moving with the same constant velocity, so these are the thing. Now finally what we'll get, actually we'll get, see this BB will get cancelled, 2 will get cancelled, so we'll get ms by m alpha, ms by m alpha, vs that will be cancelled from each other, or that will be cancelled from each other because both are same, v alpha and vs are same. So this will be q alpha by q sulfur. Okay, so here for sulfur, ms is equal to 32, that is given. M alpha will be okay, so I'm sorry, this is actually M alpha is 4. Now what about Q's? QS is actually minus electron. Q alpha হচ্ছে কি, this is 2 of electronic charge. Okay, so now it will be easier to find out. So if we put these all values, we'll get it to be, sorry, root 16, it will be root 16 will be 4. Okay, so this is how we get the answer for this. We'll go to the next question. We have now another interesting problem, that is a circular coil of radius capital R and turns N capital N has negligible resistance. Just a minute, I'll just drink some water. So you can see here the question is a circular coil. Question says a circular coil of radius capital R and turns capital N. You can see this. This is a circular coil. It has radius capital R and it has N turns. Okay, I'm writing here. So radius is equal to R and turns, number of turns, N. As shown in the schematic figure, its two ends are connected to two wires. So these are ends. So two wires are this. Okay, two wires, and those wires are again connected. See, it is hanging by those wires with its plane vertical. That means it is actually vertical to the horizontal. Okay, vertical to the horizontal. It is actually what it is doing. It is actually like standing like this vertically, like any wheel do. Okay, so this is vertical it is standing, kind of that. Okay, so this is the vertical plane. This coil has the vertical plane. Now the wires are connected to a capacitor. See, these wires are connected to a capacitor, and sorry, this is capacitor through a switch. This, and this capacitor has charge Q, and this is the switch. The coil is horizontal. Coil is in a horizontal. See, your coil is vertical, but it is within the region where there is a horizontal uniform magnetic field B. Horizontal uniform magnetic field B is 0. That means there will be a flux change or flux through this parallel to the plane of the coil. When the switch is closed, the capacitor gets discharged through the coil in a very short time. By the time the capacitor is discharged fully, the magnitude of the angular momentum gained by the coil will be, whether it is pi by 2 n cube v0 r square or any other option from this four. So this question, you can see this question is asking that by the time capacitor gets discharged fully, the magnitude of the angular momentum gained by the coil will be. So you have to find out magnetic moment. Sorry, angular momentum. Angular momentum means L. L is actually d tau dt. Delta tau delta t. This is fine. Okay. All right. See what happens in this case when the battery is closed. There will be a flow at a very narrow time or very small time interval. The charge will actually flow, the whole charge will flow. Whole charge will flow suddenly through the wire, and because of that there will be actually a torque. So there will be a torque as soon as this gets closed. Okay, as soon as, let me go to this page. Okay, I don't have figure here. So as soon as, see, this initially this capacitor is charged. Now when the circuit is getting closed, so immediately the charge will discharge through this switch to this uh, circular coil, and as current flows through this, there will be a torque. There will be a torque act on the coil. And what is this torque? How to find out that torque? We'll see that. And you know that, this, we have to find out angular momentum. Angular momentum is this, and torque is what? So torque is this, delta tau, or tau, simply tau. So this torque is actually m cross b, or mb sine theta. So m cross b or mb sine theta, that you have to write in place of tau here. Then other things are fine. See, so let me just write torque is equal to, or okay, so we know the dl dt is equal to torque. So angular momentum we have to find out. So angular momentum we can find out by integrating this tau into dt. So this is what is an important expression for this problem. Now look, what we will do, we will find out what is torque. Okay, what is torque? Let us say torque is actually m cross b, or mb sine theta, and here it is sine 90. Okay, what is m? M is I into A. I is the current passing through the coil, and A is the area of the coil, I into A. And there are n turns, so there will be n I A, and this is B0. Okay, so n I A, this is M, this is B, and sine 90 is 1. Okay, so now what is this A? A is actually n I pi capital R square. Okay, so that is the magnetic moment. Pi capital R square B0. So this is actually the torque. Now we have to find out angular momentum gained. So the torque is this Ni pi R square B0 d tau. So this will come out Ni pi R square B0, and here it will be integration of torque into, sorry, integration of torque is fine. So this dt, there is a dt here. So let us see what is the time. Time is instantaneous time, right? Then it is the answer. Okay, this time is discharged, fully discharged. Okay, when it is fully discharged. So this is actually very quick. Okay, magnitude of the angular momentum gained by the coil. Okay, by the capacitor. This you can see from here. discharge through the coil in a very short time, so that can be taken as 1 or something. Okay, then if we take this as 1, then we get pi n. Okay, so pi n I r square into v0, pi n. Okay, I think I have. Okay, okay, there is simple conceptual error. I'm just clarifying it here. Look here, this I is not a constant. Okay, I is not a constant. Okay, what is that? I is not a constant, and this is not tau. This is actually dt. This is dt, tau dt, and this is ci. This I is not a constant type because capacitor is getting discharged, so charge is always changing in the capacitor, so this current is actually not constant current. So we will actually write in terms of dt, I dt integration, that will be total charge discharge during that time. Okay, pi r square b0, and this is q. Okay, n pi r square b0 and q. So this is the answer actually. N, so pi n cube b0 r square. All right, so actually this is dl, tau is equal to dl dt. This is wrong actually. The tau is equal to dl dt, dl dt. Okay, so L will be tau dt, and what is tau? Tau is the torque on the coil. Torque on the coil, we know m cross b, or mb sine 90 degree in this case. So here we get ni ab. Ni is the total current, and this is the area. Area can be written as pi r square, and I, so this is total thing, and b0. Now what is L? You just do integration. L is equal to tau dt. So here I, as I said, current is not a constant, it is time varying, so that's why you have to integrate it over time. So that will bring you q. Okay, because you know ITT is equal to q. Okay, so this is how we get the answer for this question. Okay, now the last question for today. A light disc made of, this is actually JEE Advanced 2020. Say a light disc made of a light disc made of aluminum, which is a non-magnetic material, is kept horizontally. As you see, this is aluminum disc, and it is a non-magnetic material, is kept horizontally and is free to rotate about the axis shown in the figure. See, this can rotate any direction, it can rotate this way or this way. Okay, free to rotate about this axis. A strong magnet is held vertically at a point above the disc from its axis. See, on the axis, from the axis at any place on the disc, this magnet, this is strong magnet. As you see, strong bar magnet is placed. Okay, placed, and what is done is that this is rotating over the disk about, like sometime it will be here, sometime here, all these things. So it is rotating about the axis also. Okay, so you can see the question is a strong magnet is held vertically at the point above the disk away from its axis. On revolving the magnet about the axis of the disk will be the disk will rotate in the direction opposite to the direction of the magnet's motion. Rotate in the same direction as the direction of magnet's motion, and it will not rotate, disk will not rotate, and its temperature will remain unchanged and not rotate, but its temperature will slowly rise. So these are the options. So what will happen? See, this disk is actually free to rotate about this axis, and see what is happening. This strong bar magnet is rotated about this axis, say at various position, okay, like this. Okay, so when this is rotated, whether the disk will rotate, if it rotates, whether it will be rotating in the same direction as the magnet is rotated, or it is in the opposite direction as the magnet is rotated. Okay, opposite to the direction of rotation of the magnet. It is actually the option B, rotate in the same direction as the direction of the magnet's motion. Why? Actually, this is a fact, or this is application of one of the application of AD current. Okay, so what happens? The flux passes through this, and when its position is changed, so there will be change in the EMF, flux, and change in the flux will produce EMF, and hence AD current will be generated, and the direction of the eddy current will be such that it will oppose the relative motion. Okay, so that is the reason why it will be rotating in the same direction. See, heat will be generated due to eddy current, but these options are not correct. These will not rotate, but eddy current will be generated. That is not correct. So heat may be generated, but at the same time it will be rotated also in the same direction as the magnet's motion, and it is happening due to eddy current. Okay, we'll stop it here for today. Next day we'll further take questions from 2022 and 2023 on this particular topic and solve. So thank you for your patience. Bye for today.